In this video, I'd like to solve a simple beam problem involving a beam where inside of each element, Young's modulus is a constant, our principal moment of inertia is a constant, 2I or I, where I is given as 200 inches to the fourth power, and there are no distributed loads or body forces, only forces and moments applied at the individual elements. This is the type of problem that we can solve using the direct method. In this particular problem, I have each element is 5 feet long, so L equals 5 feet. Young's modulus is constant throughout the problem. There are forces applied at node number 2 and node number 3 of negative 5,000 pounds each. At node number 1, we are attached to a wall. We are attached as a wall mount, so not only can I not move in the y direction, I cannot bend as well. Therefore, V1 and Phi1 are both expected to be 0. As I mentioned, this is a problem that can be solved using the direct method. E and I are constant. I already know the form, or the basic form, of the local stiffness matrices. So note that here I have a principal moment of inertia of 2I. I is defined here. So when I write out the first local stiffness matrix, note that I have a 2 in front of here to denote the 2I, but the members of my matrix are all the same that we derived in a previous video. Looking at the local stiffness matrix for element number 2, I again have the same form that I previously derived. Note that there's not a 2 out here because this is simply I. All right? Now, also remember, I don't want to write them down, but remember, everything in this column corresponds to V1. Everything in this column corresponds to Phi1, V2, Phi2, V1, Phi1, V2, Phi2. Likewise, on this matrix, this corresponds to V2, Phi2, V3, Phi3, V2, Phi2, V3, Phi3. I normally would write these values, or the nodes and the values they correspond to, along the top and the bottom to help me assemble my global stiffness matrix. I'm not going to do that here, but I will use this color coding to show you how these two local stiffness matrices form the global stiffness matrix. So here's my global stiffness matrix. Note that all of the terms from green came from this local stiffness matrix. Also note that I have a 2 out here, so this 12 times 2 becomes 24. This 6L becomes 12L, and each element or each member of my local stiffness matrix gets assembled into the global stiffness matrix. These 4 terms here need to be added to these 4 terms here. So I get these 4 terms here. Everywhere else will be zeros. So if I do this math and clean this up a little bit, I'll get my global stiffness matrix like this. Now all I need to do is add my knowledge of from the boundary values, what I know of my displacement vector and my external force vector. So here, I will get my displacement vector, and I will have, I know that V1 and Phi1 are both 0. So I will get 0, 0, and I don't know V2, Phi2, V3, or Phi3. I need to solve for that. As far as my external forces go, I don't know my force at node 1. That's one of the things I'll be solving for. I also don't know the moment at node 1. These would be the reaction force and the reaction moment at the wall. That would be something I'd be trying to solve for. I do know that the forces applied at node 2 and node 3 are both 5,000. And since I wasn't given any information about applied moments at 2 and 3, I will assume that they're 0. So I will get 5,000, 0, negative 5,000, 0 to complete my force vector. Just like we did when we were looking at beam problems, my first step now is to solve for my unknown displacements. When I solve for my unknown displacement, I have no need for these two equations along the top of my vector and matrix algebra problem. What I'm going to be solving for is that these four unknown values here this vector and this vector. Once I have those and I've solved that, I can find my unknown displacements. I will find that V2 equals negative 0.105 inch. V2 is equal to 0.003 radians. V3 is equal to negative 0.345 inches, and V3 is equal to 0.0045 radians. Okay, and again, I'm solving for this 4x4 times this vector is equal to this vector. Once I have these displacements, I then can use these two equations along the top to solve for my unknown forces. So now I'm looking at this matrix times this entire vector is equal to this vector, and solving for that, I can find that F1 is equal to 10,000 pounds, as you would expect it to be, because it has to be equal and opposite of these forces, and our moment at node 1 ends up being 75 kip per foot. Okay? So fairly straightforward, not that different from what we were doing for bar problems to solve these types of simple beam problems. In our next video, we will look at a problem where I have a distributed load running along the length of my beam.